Okay, so the recording started. Let me share my screen real quick. Let me know if you guys can see that. You don't see the screen? Oh, you see it now. Okay. All right. Carlos, can you see it now? Okay, no worries. But yeah, problem one is about the probability stuff. So I hate to like throw people under the bus from the begin with, but let's see here. I wish there was like a way I could just like randomly pick someone in the chat or something. I don't know if you can do that in Zoom or not. I doubt you can. Nope. I don't think so. All right. I'll just take volunteers. I won't throw you guys under the bus, at least for this first problem. Anyone want to volunteer to walk us through problem one? Hmm. That's excellent. Yep, that's absolutely right. And let me kind of elaborate on what's going on there and also repeat it to the people who are going to be watching this online just because, um, yeah, I don't have like the mic for my computer on just because it doesn't echo and stuff. So I'll repeat it for people who are on YouTube watching. So basically, we were told that we have 1/4. You said you took 1/4 to the ninth, right? You said that the probability of finding this single like um, sequence there's only one, sequence that's unique. That unique sequence, AAA, TCG, AGT. That's only one unique sequence that you can find, right? Um, so you said the probability is 1/4, right? Um, mm-hmm. Okay, yeah. I would the way I would do it is exact same. So 1/4 to the ninth, and that gives you like 3.8. You said times 10 to the negative 6, right? Um, that's kind of like the just skipping ahead and just doing it, right? And that's absolutely right. But the way I do it, just to kind of break it down for everyone as well, just so everyone can see. So first of all, you have I don't know why this like pen thing isn't working, like the marker. Hold up, let me try and adjust my pencil. Okay, I don't know why it's not working, but basically, you have these four bases, right? A, C, T, and G. Those are four different choices that you can pick from, essentially, right? Four different choices, four different bases, right? Now, you are picking 9 places, right? You're picking 9 different like spots, essentially, right? To make a sequence of 9 monomers. So you have 9 different like boxes with 4 choices for each box, right? So the way I do these types of problems, because you're going to see a lot of these like DNA sequence type problems and um, yes, problems similar to them, but basically you have your choices as your base, right? Raised to the power of the number of boxes that you have, essentially, quote unquote boxes, right? So choices raised to the power of boxes, right? Or choices raised to the power of like selections or trials that you're going to make, right? So if I said, for example, I have a coin that I'm going to flip, right? I'm going to flip it 2 times, right? Well, I have 2 choices of what choices, but not really choice. But you can either have 2 outcomes, right? Heads or tails. Now, how many times am I flipping? How many boxes? How many trials am I doing, right? How many selections? I'm going to do it twice, right? So that takes you to 4 total outcomes if I'm flipping a coin twice, right? If I flip it 3 times, it's 2 to the third. Flip it 4 times, 2 to the fourth, right? Etc. So if I have 4 choices, right? 4 different selections I can, or four, I'll say 4 choices that I can make. A, C, T, and G. That's 4 choices raised to the number of boxes, raised to the number of trials, raised to the number of selections, right? There's 9 selections or 9 spaces to make a 9 base monomer, right? So 4 to the 9th, that's going to give you something like, what is it? 262, 144. 262,144 outcomes total, right? Now, once again, it's asking for the probability of finding just this unique sequence. So you think, okay, well, this sequence is pretty unique, right? It only happens once, right? I'm not going to see 2 of these sequences, right? It just happens once because all I'm seeing here is the 9 monomers in their places, right? And it's just one time that I can see that. It's one unique monomer, right? Or one unique DNA sequence, I mean, right? So you can also think that any other sequence, if I were to get all A's, for example, or all T's or whatever, each sequence has a probability of 1 over 262, 144, right? So any sequence, if I had all T's, all G's, all C's, if I had a mix in between, right? If I have TA, TG, C, A, whatever, right? Then any one of those unique sequences is going to only occur once, right? The total number of outcomes, the total number of sequences that I can have is based on the number of choices that I can make, right? I can choose from 4 different bases, and I have 9 spots to place those bases, right? So I have these 9 little boxes, these 9 little placeholders, right? I have 4 choices that I can make here, 4 choices that I can make there, 4 here, 4 there, 4, 4, 4, 4, 4, right? So 4 to the 9th, right? I take my number of choices that I can make, raised to the number of selections, raised to the number of spots, raised to the number of boxes, raised to the number of trials, right? 4 to the 9th gives me the total number of sequences that I can come up with. Each unique sequence only happens once. So the probability of finding this sequence, this unique sequence, would be 1 over 262,144. And that is equal to the 3.8 times 10 to the negative 6. So that's absolutely correct. Sound good for part A? Does that make sense? Does that clear up the whole, like, how to figure out the number of outcome stuff? Yes, there are 4 choices for each space. Yep. Uh, yeah, no, that'll be a long time to do that, but yeah, this is, I mean, I think this is the best way to figure out the number of outcomes particularly, and I like to figure out the number of outcomes first because then it helps to figure out the other parts there, because the other parts are just going to ask you about different types of outcomes that occur. And so if I know the number of outcomes, it's just easier to have that as my denominator and then figure out like the numerator from there, either by doing like a what's it called, um, tree diagram, right, or whatever. I can't remember what it's called, but yeah, I mean, once you have your outcomes, it just makes things a little bit easier. So figuring out the outcomes and then realizing that this sequence only happens once, right? Because it's a unique sequence. So I think that's the best way. But does that make sense as well for everyone else? Any questions about this idea of like choices raised to the power of boxes or like trials? And Christian, like, does that, I don't know, like maybe that part is just easy. Like is, I don't know, is it clearing up anything at all? Or like, I don't know. I got you. Okay. All right. So hopefully when we get to C, then it'll clear up a little bit. But yeah. All right. But yeah, anybody want to volunteer for B then? Okay. Mm-hmm. All right, so, yep, exactly. So since this is, once again, a unique sequence there, they're not asking for a sequence that has like at least three A's, for example, or at least three T's or something like that. Those sequences are a little bit less unique. They're just straight out just giving you what the sequence is. And if they're giving you what the sequence is, there's only one way for that sequence to happen, right? Now, if they were to say like something like this for part C, like what's the probability of finding a sequence of length 9 with no A's in it? Okay, well then you have like a bunch of different options that they can choose from, right? You can have something with all C's, all G's, all T's, a mix of C, T's, and G's, right? To have something with no A's in it. So when they're giving you a sequence like this, they're literally telling you this is just one sequence, right? This is a unique sequence. And so that can only happen once out of all the outcomes. So that's 1 out of 262,144. And that still gives us our 3.8 times 10 to the negative 6 for our probability of finding that specific sequence, right? Because that sequence only happens once. It's unique. Now for part C, what are we thinking about part C? Okay, go ahead, Christian. Mm-hmm. Exactly. Yep. Excellent. So since we only have three options that we can choose from now, right? We can kind of repeat almost in a sense what we did for part A. So now it's looking for the amount of outcomes based on the fact that we only have three choices. So if we only have three choices, right, and we have 9 spots to make those choices, then we have 3 to the ninth outcomes, and those don't have A's in them, right? Because we only said, okay, well, A is no longer. We have C, T, and G. Those are the three choices that we can choose from for the 9 different spots that we talked about here, right? So if we have, instead of 4, 4, 4, 4, we have 3 all the way. We just take 3 to the ninth exactly, and then divided by the total number of outcomes that we came up with A, right? Because we want to figure out still, right? We imagine that we still have all 4 choices. It's just that we're selecting to ignore A, or the ones that have A's in them, right? So 3 to the ninth gives us the outcomes that do have A's, right? And 4 to the ninth gives us the total number of outcomes when we have 4 choices. So 3 to the ninth divided by 4 to the ninth, or essentially 3 over 4 to the ninth, right? And then that's going to give you around 0.075, I think, something like that. Is that about what you guys got? Hold up, let me double check here. Okay, cool. Yeah, exactly. So you have to divide your desirable outcomes essentially. So we want to look at the outcomes that don't have A's, and so the total number of outcomes that don't have A's would be the number of choices raised to the number of boxes. So we only have 3 choices, C, T, and G. We have 9 spots to choose from, right, for the 9 sequence. So 3 to the ninth gives us the outcomes that don't have A's, and we have to divide that by the total number of outcomes, right, originally, because we still have A as an available, you know, choice. It's just that we're selecting for, or we're only looking at the ones that don't have A's. So you still have to divide by the total number of outcomes, including A's. Does that make sense? Okay, cool. So that's C. Now, D is where it gets a little bit tricky. But I think the best way maybe to think about this is if you were to kind of forget the the 9 like sequence stuff for a second and just think about if we were to make like a huge like tree diagram for this, right? You guys have seen, I don't know if you've seen tree diagrams in stats or not, but if you have A, T, G, and C, right? These are your initial choices, right? So I can choose A, T, G, or C for the first box, for example. Now, for the second box, I start drawing these little branches, right? And then for that second box, I can either choose, once again, A, T, G, or C. For the second box, right, I can start off. So essentially, what I'm trying to say here is that this is your first box, this is your second, afterwards is your third, fourth, fifth, sixth, seventh, eighth, ninth, right? So for the first box, right, I can also have T as my choice. And so for the second one, I can have A, T, G, C as well. A, T, G, C as well, right? A, T, G, C. So this is giving us the first box or the first spot, and these choices are giving us the second spots, right? So let's think about if we were to only stop at 2 spots, right? We just want an easy number to work with, kind of, right? So if we have 2 spots and we have 4 choices for each of those spots, we have 4 choices, right, raised to the power of 2 spots. That gives us 16 total outcomes, right? Now, if we were to look at this tree diagram, because just like I said, it's just easier to kind of think about it with less numbers and stuff, so you can kind of extrapolate it and kind of extend it to the larger number. But if you look at here, I want to see this is the first spot, like I said. So they want you to look at the probability of finding a sequence of length 9 with an A in the first spot, right? So in the first spot, the probability of having the first spot being an A would be 1 out of 4, right? So there's only one possibility of getting an A for the first spot, right? How about the second spot? What's the probability of getting, or essentially, like if I look at this second spot here, right? Because these are a whole nother set of outcomes. I have AA, AT, AG, and AC, for example, right? Which is what I'm looking at here. So those are 4 outcomes there that start with A, right? So if I look at it, there are 4 outcomes that start with A. Divided by 16 total outcomes, right? Now, if I continue this tree diagram along, right, I'm going to increase in the number of my outcomes. It might be 4 to the third now, which is 64 outcomes, right? But the thing is, these outcomes that include A as the first spot is going to increase as well. And it's going to increase, like, I want to say proportionally necessarily, but basically once we look at here, these first 2 spots, is just like I said, it's a lot easier to look at the first 2 spots. You can see that there's 4 outcomes out of 16, and that's going to extend, that probability is going to extend for the rest of them. So 4 out of 16 is 1 out of 4, right? Probability of finding a sequence of length 9 with an A in the first spot would just be 1 out of 4, 25%. 25% of all of those outcomes will have an A in the first spot. Because if we extend this, right, and we have those 64 outcomes, we're going to notice that 16 of them now are going to start off with an A. Because we could have A, AAT, AAG, AAC, for example, right? ATA, right? And we can continue along and we'll see that 16 of them now. So it's a fixed probability based on the first one here. We notice that for the first spot, there's a 1 out of 4 probability to get an A in that spot. Now for the second spot, right? Well, there's 4. If we're looking at both spots right here, right? Both spots, there's 16 total outcomes, right? Now, 4 of them contain an A in the first spot, which is A, AT, AG, AC, right? 4 of them contain an A in the first spot. We went from 1 of them containing to 4 of them. We only had 1 outcome here, so we said for the first spot it could be A, T, G, or C, right? Then only 1 outcome here has an A in the first spot, right? Because you're only looking at 1 spot, so it's 1 out of 4. For the second spot, right, we have outcomes like AA, AT, AG, and AC, right? You started off with A here, and now you might have T, G, and C as well in that second spot, or another A. So you can see here that's 4 outcomes now that have an A starting off out of 16 total, right? So it's like 1 out of 4, right? And you multiply now by 4 on the bottom here. You multiply by another 4, another 4 here, another 4 there, right? And so you can see then, after 3 trials, like we said, we have 16 out of 64. Well, what's 16 out of 64? Still 1/4. If I multiply by 4 on both, top and bottom again, right? I'll get what? 16 times 4 is 64, right? And then multiply by another 4 is 256. So if I do 64 divided by 256, I'm still going to get that 1/4. So it's a fixed probability from the beginning. So the probability of finding a sequence of length 9 with an A in the first spot should be 1 out of 4 based on, for that first spot, there's only 1 outcome that's going to give us, out of 4, an A in the first spot. So that probability is fixed and it kind of continues along, right? Now, with regards to kind of like describing it a little bit better, I think, just so you guys have like a way to kind of describe the answer, I guess, or just give an explanation essentially. So, I don't know, like, I'm trying to think of something that'd be a little bit better, but that's how I figured out part D. So I took 2 spots, for example, figured out the total number of outcomes, and showed that 4 of them out of 16 will have an A as the first spot, and that'll continue along. And so I guess you could say like the probability of having an A in the first spot is just 1 out of 4, and that continues regardless, because you could have whatever you want for the rest of the spots, right? I could have A, T, G, C, A, T, G, C, whatever, right? That's 6, 7, 8, okay. And then another A, for example. Well, that counts, regardless if I have 3 A's, 4 A's, whatever, that counts as a sequence that starts off in the first spot with an A. So if I have 4 choices, 1 of them starts off with an A, right? That's going to be my probability for like the whole system, for the whole number of outcomes. 1/4. 25% of all of the outcomes will start off with an A, because I started off with the first one, right? For the first spot, there were 4 choices. 1 of them has an A. So 1 out of 4, right? And that'll continue along. Does that kind of make sense for part D? Yeah, go ahead. No, no, that's a great question. You can just focus on the first spot. I just figured I could use the second spot as well, just to show that as you go, like regardless of of outcomes, regardless of number of spots, that probability is going to be fixed, right? Because you started off with the first spot. There's only one outcome. There's only one choice. There's only one A, right? Um, Out of those four choices, that's going to start off with an A at the beginning, right? So that probability is fixed, and it kind of goes throughout the whole sequence or the whole system. So you can just leave it at the first spot if you want to. But I just chose two spots just to kind of show that if I have the first spot, it's 1 out of 4. If I have the second spot, it's still 4 out of 16, which is 1 out of 4, right? Third spot, still the same thing. So you can focus on the first one only if you want. That's fine. Mm-hmm. But yeah. So hopefully that kind of makes sense. It's a little bit messy here. Let me kind of erase some of this real quick. Right? But yeah, hopefully that kind of clears things up for part D. Christian, did that make sense a little bit? Okay, cool. Yeah, I mean, I don't know if there's like a better way to kind of, maybe I'm just like saying it wrong or something. Maybe I just am missing like a statistical term to describe what's going on here exactly. But really, if the first spot, if it's only 1 out of 4 um, to get an A, right? In the first spot, there's only one A for the 4 choices that you can choose for the first spot, then that kind of probability continues along throughout the system. So, yeah. But that's problem 1. I'll look into D again. Just like I know, I have a feeling this sounds very familiar to something, or at least like a specific term or something that I'm missing in stats. But I might look it up later, and if I can explain it a little bit better, I'll send you guys an updated explanation for that. But like generally, that's what's going on here for part D. But yeah, that's about as difficult as the probability is going to get, honestly, with this chapter. Um, and to reassure you guys, you know what? I might as well. Let me hold up. Let me see if I can pull up a my quiz here. Hold up. Let me stop sharing real quick and show you guys the quiz that I took for this chapter. And it's literally like it was just throwing some dice, and that was it. That was the probability. So very small numbers, easy to work with. I mean, worst case scenario, I think they might pull the DNA bases and stuff, but even then, like, I don't expect them to have like very huge numbers or anything like that, because that's not the goal, right? That's not the goal, to test you guys on like probability knowledge and stuff. Give me 1 second here. Let me pull it up. Okay, there we go. Okay, hopefully you guys can see that real quick. Let me know if you can't. Okay, you can. All right. So yeah, it says 2 fair 6-sided dice are rolled together. What are the total number of outcomes, right? So you have, for each dice, right, or for each die, right, you have 6 numbers that you can choose from, basically, quote unquote choose, right? And then the number of trials and the number of selections and the number of spots would be 2, right? Because you're rolling it twice. Or essentially, it's not really, I mean, you're rolling 2 of them, basically, right? You're not rolling twice necessarily, you're rolling 2 of them. And so 6 squared, that would give you 36 total outcomes, right? Probability of rolling 1s on both dice, you just take 1 and 1, right? That'd be 1 out of 36. That's just one option, right? That's one sequence, for example. What is probability the numbers rolled up add up to a total of 9? So you just figure out like what two selections of numbers will add up to a total of 9. 5 and 4, 4 and 5, 6 and 3, 3 and 6, right? That's 4 outcomes out of the 36, and you're done. That's the gist of the probability that we saw. And then the second problem was just basically like the last problem in their written homework here that I'll go over. Very, very like just simple math, and it's just the issue is like making sure that you got your numbers correct. That's it. But does that give you guys any reassurance at all or comfort? Hopefully does. I don't know. For the quiz, yeah, one sec. Yeah, I mean, it's like, it's not horrible. You get like literally part A was 2 points. You're just converting from, what was it, Kelvin to Fahrenheit, and that was it. That's 2 points if you can convert between different temperature scales. Part B is just figuring out RMS speed, and you'll do that a bunch here, so it's not horrible. But like I said, for the probability, I really hope they just don't screw you guys over and give you something difficult. But I mean, you guys can see here, like, it's not horrible. And generally this semester, like, your quizzes have been similar to mine in difficulty. I think last semester's quizzes were by far harder. But like, you can see the probability isn't horrible. Like, it all kind of makes sense, and it's quick because you can only do it in 20 minutes, right? Or whatever, how long the quiz is. So for them, like, they don't want you to think about the probability stuff too long, because really what's more important is the RMS speed and temperature stuff, because I don't think you get a probability problem on your exam. I think it's just this stuff. I don't remember a probability problem on the third exam. It was literally whatever was from this chapter was just concerning the RMS speed stuff. That's the more important concept to learn here, because you're going to delve into probability in 132 a lot more in depth. So they're just giving you a foundation here. But yeah, that's the quiz there. Hopefully that gives you some reassurance and comfort. But going back to the quiz here, or the written homework. So moving on from part 1, we have part 2, or problem 2 here, random motion of 100 particles. So a scientist is measuring the random motion of 100 small particles in a long, very thin tube. With the aid of time-lapse photography, she locates all the particles at a given time, and again 20 seconds later, she measures the displacements all in the positive or negative x direction, and counts the number of particles that travel different distances from their starting points. Motion in one direction is arbitrarily called negative, and in the opposite direction it's positive. Following table is obtained. So they're asking you for part A, what is the probability that one of the molecules chosen at random has traveled 15 micrometers or more from its starting location? Anyone want to volunteer for this one? Or I might just call it a name. I don't know. Which probabilities, though? That's the question. Cool, yeah. So would we add up this probability, for example? Theoretically you could do that, right? But we don't know exactly what the probability is to travel exactly 15 micrometers, for example, or the probability to travel 16 micrometers, for example, right? We don't know all those probabilities in between, so it's tough for us to figure out the total probability for those in between distances. But we do know that we have negative 20 here, that's 15 micrometers or more, and negative 30 here, that's 15 micrometers or more. So there are these two probabilities, and then there's these two probabilities as well, right? So like you said, absolutely right, we can add them up together. 0.01 plus 0.06 plus 0.06 plus 0.01, right? And that gives us 0.14. Now, could there be probabilities, right, for those in between distances? Maybe, but we'd have to adjust the rest of our probabilities because you see here that all of these probabilities add up to 1. So we can't just like say, okay, well, traveling 15 micrometers exactly is going to be 0.07, for example. Well, then you'd have a total probability of 1.07, which you can't have that. So you would kind of have to adjust your probabilities. And basically, like, she would essentially have to redo her experiment to figure out the probabilities for each little distance in between. But yeah, I mean, or maybe she didn't have any of the molecules, for example, travel exactly 15 or exactly 16 or something. Maybe they were all just like she has them here, that they were all around these displacements, right? Nothing really in between. So all we can do is, like what Matthew said, we can just add up the probabilities that would be pertinent to the displacements that would be 15 or more. And so we have 20 and 30, and we have 20 and 30, both positive x and negative x directions. So you'd have a probability of 0.14 here. Does that make sense? Okay. Part B now is drawing a histogram of the probability distribution given describing the molecule's displacements. Okay. Weird sentence. Okay. I now understand what it meant. Okay. So we're supposed to draw a histogram basically of these values, right, for this distribution here. So for a histogram, it has probability on the y-axis, right, your percentages, right, or your decimal values for your probability. And then you have your different values on the bottom here, your range of values. So, I mean, I don't think they're very strict about, at least I don't remember them being very strict, the TAs, about how you graph this, because some people just went ahead and drew bar graphs. Like, they just draw like, okay, this is 0.2, for example, and then this is like 0.3 or whatever, right, for each little displacement. Now, me being the stats person that I was back when I took physics, one of the main things that I remember from stats, it was like a big no-no with histograms, or at least like a big like thing to remember, was that your, like, I can't remember exactly how to say it, but I think it was like whenever you have your range of values, you have, I guess, like the desired value that you want in the middle, like right in the middle. So if I wanted to look at the value of negative 30 and its probability, then I'd have to have a bar that went from negative 35 to negative 25, right? So that's a distance right there of 10, or a range of 10 micrometers, right? And right there in the middle is going to be negative 30. I think that was like one of the main things with how to set up a histogram, is to make sure that the value that you want or that's in question would be the one in the middle of your bar graph range. And that's how, or histogram range, that's how histograms work. They'll have ranges of values, not just like, because people would just say negative 30, negative 20, negative 10, and then they would just like draw the graph, and they would have spaces in between too, which is another big no-no. You should have your histogram set up in a way where they're all touching. All the bars are touching each other like this, kind of, right? So it's very tedious, but roughly I had my probability here at the bottom 0, and I kind of counted every 2 boxes as 0.1. So this would be 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, and 1 up top. there just to make it as to scale as possible, or at least like to fill up the whole graph, essentially. Then at the bottom here, I have starting off from negative 35 to negative 25 over here, so I can have negative 30 in the middle. And then from negative 25 to, or hold up, did I mess something up? No, I'm good. I went by every twos. Negative 25 to negative 15, and then from negative 15 to negative 5, right? And then from negative 5 to 5, from 5 to 15, 15 to 25, and from 25 to 35. So a space or a range of 10 in between each time. That way, right in the middle would be these values that I have over here. That's how I did it personally. I'm not sure how strict they are, but I got full points for this, and so if you want to follow the same way, I think it'd be a pretty safe bet. This is like stats approved, so if we look at the negative 30 option, right, negative 30 displacement, it was 0.01 for its probability, so that's like down here kind of. Oops, I extended it a little too long there. So there to here. Oops, I did it again, damn it. All right, there, something like that. Negative 35, negative 25. And then for 25 to 15, right, we had 20, and that's 0.06. So that might be around like a little bit more than halfway between 0 and 0.10. From negative 15 to negative 5, well, we have negative 10 right in the middle. So that gives us a probability of 0.23. That shoots up to somewhere around here maybe. Right? From negative 5 to 5, that puts 0 right there in the middle. And that has a probability of 40, so that shoots up even more. Right? 5 to 15, we have 10 in the middle, and that's another 0.23. It's pretty symmetrical at this point. 15 to 25, you have 20 right in the middle, that's 0.06. Yeah, it's pretty symmetrical at that point. There, and another 0.01 or whatever it is there. That's how you would, or at least how I would draw the histogram. All the bars touching each other, no spaces in between. Your range of values should be spaced in a way where you have the value on the table right in the middle. So negative 35 to negative 25, so that negative 30 would be exactly in the middle. I just don't remember the exact rule, but this was like one of the biggest things that like people lost points off for in AP Stats in high school. So like this is stats approved. I'm fairly certain like this is how to draw a histogram properly. Otherwise I wouldn't have done well in that class. But negative 35, negative 25, you have your value in the middle there, and then your probabilities, I spaced them out. Every two boxes I had 0.1, so I could cover the entire y-axis there. So, any questions about part B, how I drew it? Nope. Okay. So that's problem 2. Problem 3, modeling a random walk, right? Mathematician decides to test probability by doing a random walk. He flips a fair coin and takes a 1 meter step right if it's heads, and a 1 meter step left if it's tails. After any number of coin tosses, he's at position X. Take X equals 0 to be his starting location. Okay. Well, after flipping the coin 3 times, what are the possible final X positions of the mathematician? For each possible final position, list exactly what sequence or sequences of steps led to that position. And then, okay, so example RRR would be a sequence corresponding to the final position of positive 3 meters. So we want to list out, right, all of the different positions that we can have. So we can go, like they said, RRR, so that's 3 steps to the right. So that's what? flipping heads 3 times, right? Right if it's heads, left if it's tails. So that's stepping to the right 3 times for a final position of 3 meters. Or you could do LLL, for example, which is -3 meters, and that's 3 steps to the left. So basically what you want to do is list out all the different like possible combination of steps, and then right next to them tell what the final distance is or final position, right? So I went R, L, R, right? Right, left, right. Well, that's at a distance of +1 meter, for example. Right? So that's the gist of what we're doing for part A. Now the big question is here. Oh, is the screen frozen? Okay, 1 second. Okay, can you guys see it now? Yeah. So I was writing the RR, LLL. So basically what we want to do is just write down the different positions, the different sequences, and list the final position at each sequence. But the question here is, can anybody tell me how many total outcomes are we looking for? Because you could be like doing this for a while and not notice that you might have done the same sequence twice or something. 8. Okay, how did you get 8? Exactly, yep, 2 to the third. So that's 2 outcomes, heads or tails, right? Raised to the power of number of trials, or number of boxes, or number of spots, or number of selections, right? So we flipped it 3 times, that's 3 trials, right? So 2 choices raised to the power of 3 trials. That gives us total of 8 outcomes, right? So anyone want to walk me through which trials you guys had for part A? Okay, yeah, go ahead, Christian. Okay. Hold up. RLL is -1 meter, and then what was after that? Mm-hmm. Okay, excellent. RRR, +3, RRL, RLR, RLL, LRL, LLR, LRR, LLL. If anyone were to play that back on YouTube, it just sounded like I was just going nuts. All right, so that's the those are the options that you should have for part A. Yep, each final position. Write down the position next to the outcome. So looks good to me. All right, let me just make sure all these positions add up as well. Yep. RL, okay. +1 RLR. Okay, cool. All right. Now, oh, right here. That's trials. Yep. Yeah, I just took 2 choices raised to the power of 3 trials to give me 8 possible outcomes. Yep. For part B, what is the probability of each of the final positions? So we're looking for the probability of going 3 meters, for example, probability of going 1 meter, for example, or going -1 meter, right? Because we have what? We have two situations where we traveled 3 meters, right? But it's one is 3, one is -3. So we want to separate them out. So x right here, probably x could be, we list out our different possibilities. We could have +3, we could have -3, we could have +1, we could have -1, right? Those are the possibilities that we have. Let's see here. I'll call on someone this time. Carlos, what is the probability did you have? Or if you could, walk us through it as well if you don't have it yet. But how would you get the probability for each of those positions? Yeah, if you want to just go through one of them, yeah. So this one. If you're not really sure, no worries. I don't mean to put you on the spot there. If you're not really sure, then we can maybe come back to you later. For example, if we can figure out the first one, and then maybe that'll give you an idea. No, no worries, no worries. Anybody else want to give it a shot for at least one of them? Mm-hmm. Yep, exactly. And if you want, you can just leave it as a fraction as well. 3 divided by 8, 3 over 8. You can leave it as that as well. But yeah, that's absolutely right. Yeah, go ahead, Carlos. Okay. Yep. 3 out of 8 for probability of getting -1. Let me see here. I'll call on someone else. Rachel, do you have the one for 3? Yep. And then, yeah, you said, yeah, x equals -3 as well as the same because you either have +3 and that's one of them, or -3 and that's one of them as well. There's only 2 options there. And so that's another 1 out of 8 for x equals -3. And yeah, I would break them up. I wouldn't put the 3's together because they, I don't know if they indicated necessarily, but that's how I did it. And I wouldn't group them together because you can't say, like, especially for probabilities, you can't say, like, x equals 3 and -3. That's just, like, that'll throw things off. But yeah, probability of x equals 3 is 1/8. Probability of x equals -3 is 1/8. So that's part B. Now, here's where things get a little interesting for part C. These are the calculation heavy questions. These are really good practice because it's going to help us figure out problem 4, and it's going to be hopefully similar ideas to what you're going to get on the quiz. Just basic math. If the only thing is you just hopefully don't mess up these two values here. The idea with the average squared in, like, I don't even know how to, like, really say it honestly. This would be like the best way I can say it is just like by writing out the equation for it. So to figure out the average here, this would be like taking your average, right, whatever your average is at the end, and then squaring it, right? Now, for this one right here, it's as if I was taking, okay, if I have 3 and 4, right? Well, that gives me an average of 3.5, right? 7 divided by 2, that's 3.5, right? If I had 3 marbles and the other person had 4 marbles, okay, what's the average number of marbles between us? 3.5 marbles, right? Now, if I wanted to square that as well, in order to get this value, this average squared, I would do 3.5 and then square it. Now for this average squared, where the squared is inside the brackets, right? Then what I would do is actually take the first value, square it, and the second value, square it, and then divide, right? That's the idea, kind of. So it's like you're squaring your values first for this one, and then here you're squaring them at the end for the other one. That's kind of the concept here, or at least the idea. Now in practice, with regards to the values, right, and their probabilities, if we wanted to figure out what this one is, the average squared with the exponents outside the brackets, it's the sum of the value times the probability of getting that value, right? And then just squaring it at that point. But for this one right here, where the squared or the exponent is inside the brackets, right? You take the sum of the values squared times their probability. Right? That's how you do it. Now, for the first one, if we go by the values, right, and then we square them at the end, the first value, let's go 3. 3, that's the first value that we can get. For example, 3 meters, that's our displacement. The probability of getting a displacement of 3 meters is 1/8. So we multiply the value itself by the probability of getting that value. Now how about getting a value of 1, right? There's a probability of 3/8 there. So 1 times 3/8. Well, how about now getting a value of -3? Well, the value there is we have to do -3 or plus -3, right? Because we want to add up the values times their probabilities. So the value here is -3, and it has a probability of 1/8. And then we also have a value of -1, and it has a value or a probability of 1/8. Right? So you can see here that essentially this will cancel out with this one, and this cancels out with this, right? 3/8, or hold up, did I write that wrong? Oh yeah, I wrote 1/8 here instead of 3/8, my bad. There we go. Probability of -1 is 3/8. Yep, go ahead. Yeah, you can write the probability as decimal. So this would be 0.125. And what is this? 3/8 is what? I forgot. 0.375. Cool. Yeah, this is 0.375. So you can do that as well. Yep. 0.125, and this is 0.375, right? So you can see though that these will end up canceling out because this would be a positive 0.125. This would be a negative 0.125. This is positive 0.375, negative 0.375, right? So they end up canceling each other out, actually. And what you get is an average value of 0. And if you square that, it's still 0. Right? Now, for this one, go ahead, yeah. You can do it with the squared as well. Yeah, I mean, I would put it with the squared just because that shows that you squared it at the end, and I mean, well, 0 squared is 0, so. Yeah, essentially, yeah. And then for this second one here, how would it be different from this first one? How would this second one be different? Anybody have any ideas? Or at least can you like roughly say real quick, verbally at least, how or what addition or what change we would make to this first equation to get us this second equation? No, go ahead, sorry. Yep, exactly. Yeah, we'd square each value. So we'd raise these each one to the power of 2, right? So 3 squared times 1/8 plus 1 squared times 3/8 minus 3 squared times 1/8, right? Minus 1 squared times 3/8, right? Now, be very careful when you're plugging this in your calculator. I would say for these last two parts, because they're negatives, the way I would add them together, I'd say plus -3 squared like that, right? So that gives you positive 9 times 1/8, and then plus -1 squared like that times 3/8. Oops. Let me move this over a little bit. Oops. So that gives you your average squared there, and that's equal to 3, right? Now, if we want our RMS average, root mean squared average, how do we get that? Yeah, go ahead. So I believe it's just going to be easier for your calculator to, like, you add in and then have a parentheses, -3, another parentheses, and square it, because that will give you plus 9 here. So -3 squared is 9, right? -3 times -3, that's plus 9. But if you were to write minus 3 squared like that, right? Maybe your calculator will do the exponents first, right? Because it's PEMDAS. They'll do the exponents first. And so 3 squared, that'll give you -9 instead. And that'll throw things off. And that's not what you want to do. So I want to make sure that I'm adding in that value squared. And that value was -3. I square that value, it becomes positive 9. I don't want it to be -9. I want it to be positive 9 because I squared it, right? When I square it, I get rid of the negative sign, right? So when I throw it into parentheses like that, it preserves the value. And when I square it, I get the right one. Does that make sense? Yep. Yeah, you have to throw them in parentheses first, then square them so you can like get rid of the negative sign. Because the whole point of squaring them right there would just be getting rid of the negative signs. But if you leave them out, if you leave the negative signs outside of parentheses, then you get -9 instead of positive 9, and that'll really throw off your answer. But that gives you your average squared equals 3. Now XRMS, anybody have an idea how to get XRMS? I drew the square root sign already, so that kind of gives you a hint. So that would be actually your, foreshadowing, that would be the exact same answer, but you're close. So what you said there with the 3 minus 0, that would have been your standard deviation. But then for the, yeah, go ahead, Matthew, sorry. Yep, exactly. So you take just the square root of this value right here. So just the square root of 3. Because the XRMS is equal to the square root of the average squared with the average, or the exponent being on the inside of the brackets. So this value right here we already figured that out to be 3, right? They're not asking us for the square root of the average squared where the exponent was on the outside. They're asking for the one that has the exponent on the inside of the brackets. And that we already figured out to be 3, right? So you just take the square root of 3, and that's your RMS. Now for standard, yeah, go ahead. It would just be 3, it would be in meters because this whole thing was in meters from the beginning. Yep, because we're looking at for like, these are just average like values, so it would be 3 meters, square root of 3 meters like that. Yep. And then for standard dev, right? Zahra already said earlier that it was going to be our x squared, basically, right? With the exponent on the inside minus then our average squared with the exponent on the outside. And so that's now 3 minus 0, which is still root 3. So for standard dev, you take your average squared with the brackets on the inside minus the average squared with the exponent, or what did I say for the first? Okay, for the standard dev, you take the square root of the average squared with the exponent on the inside of the brackets minus the average squared with the exponents outside of the brackets. So x squared inside minus x squared outside, and then take the square root, and that gives you root 3, because we already figured out this part right here, and then this over there. That gives you root 3. Yep, that's part C there for problem 3. Any questions at all about this? Yeah. Yep. Because I mean, think about it, like, especially for standard dev, like in your lab and stuff, like you might see something like plus or minus 3 meters or something, right? Or plus or minus 0.1 meter, right? So the units are always going to be in the original units. So if my average is 0 meters, for example, or my average squared is 3 meters, or my standard dev is plus or minus 1.1 meters, right? It's all going to be in meters, just to kind of describe the distribution of the values that we have here. Our values are in meters, so when we're describing the distribution, our units should be in meters. So hopefully that makes sense for problem 3. For problem 4 now, it's asking us what is the average speed, or my bad, no, I was reading off part A, I think, already, yeah. Instead of reading the introduction first, my bad. Random motion container of gas filled with helium with a molecular mass of 4 Daltons, or 6.64 times 10 to the negative 27 kilograms, is measured to have the distribution of molecular speeds shown in the histogram to the right. What is the average speed? Not RMS speed, just what is the average speed of the helium molecules in this container. So VRMS would have been this. That would be your VRMS, which is what they're asking for in part B, actually. So that'd be like your speed squared with the exponents inside the brackets. But they're just asking for the average speed. And so the average speed is just the average speed, right? Speed with the brackets. And so remember, if we said that the average distance, right, or average displacement, the way to get it was the sum of the value times the probability of the value, then this would be the same thing here, right? It would be the sum of each velocity or speed value, right, times the probability of getting that speed value. Yeah, go ahead. Oh, is the screen frozen? Okay, hold up. Let me stop sharing and then let me reshare again real quick. Okay, is that better? Okay. Yeah, it would be the sum of the speed values times the probability of getting that speed, right? So it says you may approximate all the molecules in each bin as having the speed equal to the central value. That's what I was talking about earlier for the stats, like how to set up a histogram. It says you may approximate all the molecules in each bin as having the speed equal to the central value. So that's why I put the central value there for that histogram that we drew earlier. So that means that all the molecules in the 0 to 200 bracket, right, have a speed of 100 meters per second. So this would be 100. Oh, that's hard to read. That'd be 100. This would be 300, 500, 700, for example, 900, and then 1,100 over here, right? So the speed should just be the value in the middle, right? So how would we figure out this average speed then? What value would we start off with, just so I know that you guys are understanding what's going on here? Yep, excellent. So we take your initial speed, right? That was the 100, right, in the middle there, and then times the probability, right, or the percentage of molecules here. And so there's 6% right there, right, between 4 and 8, right there in the middle, 6. That's 6%, which is 0.06. And I would actually recommend putting units there so you don't get points off. Meters per second times a probability of 0.06. And then what's next? Anyone can go, honestly. Like, you just name out values. Yep. And then, oops. Yep, 500 meters per second times 0.36. Cool. And we add over here another one. Cool. And what's the last one? Excellent. Awesome job. Yep. Perfect. That's your average speed there. So you take each little speed value, right, for each little bar there, 100, 300, 500, 700, 900, 1100, right, multiplying by the probabilities, and that gives us, when we add all those together, that gives us our average speed. And so our average speed here should just be 474 meters per second, right? Now, if we look at the RMS speed, for the RMS speed here now, right, it's going to be very similar, like I said earlier, but there's going to be one big change because VRMS is equal to the square root of V squared with the exponent on the inside of the bracket. So how do we get this value right here? What would that be in a similar notation to this one, like the summation notation here? How do we write that out? Any ideas as to how we would set it up for the summation? Mm-hmm. Exactly. Yep. So if we do that, that should give us our V squared, right? And essentially, in order to get VRMS, we just take the square root of this, right? So the only adjustment really that we would have to make to this equation up top here is literally just to square every single value. So, and then obviously take the square root of that entire answer. So it would literally just look like square root of this big giant lump of stuff, 100 And for sake of space, I won't write the units. But 100 squared times 0.06, 300 squared times 0.34, 500 squared times 0.36, 700 squared times 0.17, 900 squared times 0.05, and then if we really stretch here, hold up. There we go, 900 squared, and then 1100 squared times 0.02, right? And that's all under the root there, because this is what we're trying to figure out, this equation here on the inside. That's going to give us the average squared with the exponent on the inside of the bracket, right? And then we have to take the square root of that to get the RMS speed. So for VRMS, someone let me know what they got. Yep, sounds good to me. 518.8 meters per second for your VRMS. Everyone agree with that? All right. So that B. Part C now is just asking you for the temperature of the helium gas in the container. Well, that's weird, right? How do we go from speed to temperature and all that, right? That's a question you have to ask yourself. So how does speed relate to temperature? Now, from what you learned, right, you know that the average kinetic energy gives you the temperature, right? The temperature in and of itself, the definition of temperature is the average kinetic energy of a substance, right? Or particles, right? Or whatever. So knowing that definition or that relationship, there are two equations that we can help relate speed and temperature here. So it all comes back to average kinetic energy, right? What is kinetic energy equal to? This is from like just really just from like last 2 weeks or something, the energy stuff. Well, yes, I'll get to the 3/2 kVt, but yeah, average kinetic energy is equal to 3/2 kVt. But also, what does it equal from the energy stuff from like 2 weeks ago? Yep, 1/2 mv squared. Now, the idea here with this particular equation is that you have to notice and you have to know that the v here, yes, it's v squared, right? But the v in question here is actually the RMS speed. So even though that like the equation shows up on your equation sheet and stuff as, or even on your slides as this, as your average squared, it's really your RMS speed. So like if you're going back and plugging things in, I wouldn't plug in 474 like as my average and then I square it. I plug in my RMS speed instead. So 518.8 and then square it. So your V in this equation refers to the RMS speed, not the average speed. Which is a little confusing because you're normally used to the RMS speed being the square root of like this stuff here, right? The average squared with the brackets on the inside. And that the bracket or the exponent on the outside would just mean your average squared. But for this equation, there's a distinction that the speed used in this equation is the RMS speed, all right? That's one of the most important things about this equation here for this chapter. To notice that the speed here is the RMS speed, not the average speed, it's the RMS speed. So you take the RMS speed and square it. Now, this is all equal as well to 3/2 kVt. That's the relationship here. Well, then we have T and we have V, right? So we can kind of rearrange some things around to isolate T. So T is then equal to, if we multiply the 2 over, that cancels out with the 1/2, right? So we just have mv squared on the other side. If we divide over 3 and kb, that gives us our T. So you multiply over 2. 2 times 1/2 is 1. Divide by 3, mv squared divided by 3, and you divide by kb as well. So mv squared divided by 3 kb gives us our t. And so they gave us the mass from earlier. They said it was 4 Daltons, or 6.64 times 10 to the negative 27 kilograms, right? 6.64 times 10 to the negative 27 kilograms. V squared, right? We said that was the RMS speed that we have to use. So that's 518.8 meters per second. And then we square that as well. And then divided by 3 times Boltzmann's constant, which is 1.38 times 10 to the negative 23 joules per Kelvin, right? So total, what should that give us for the temperature here? And remember, this temperature should be in kelvins, or Kelvin. What is the temperature? Just the temperature of the helium gas in Kelvin. Any takers for this part? All right, 43.2. Yep, exactly. 43.2 Kelvin. That should give you your temperature there for C. So that's problem 4 there. I'm betting you might see something like this on the quiz, definitely on the exam. I've already actually uploaded the exam on Google Drive, exam 3. You guys can check that out already. I have the practice exam uploaded and the midterm that I took as well. So that's problem 4. Problem 3, I don't know if there was something like this on the exam or not, but maybe this would be fair game for the quiz, because it's a very quick, kind of simple probability type problem. But I was honestly, at least for this problem 1, I would just hope and pray that this isn't on there, because the first A, B, and even C to a certain extent isn't bad, but then when they start giving you conditions for part D, or they're just a little bit weird, it gets kind of hard to think about. But yeah, I mean, the online homework, especially for this, gives a lot of good practice for it. You guys already have the answer for that as well, so it helps you kind of to think through some of these problems. And then I'm trying to think. So for probability, let me link my old stats book. I'll go ahead as far as giving you guys the link to it as well on Z Library or whatever it is, so you guys have access to that stats book, because that stats book was phenomenal. And there's a really good section teaching you about probability. It might even give you a few tips and tricks to kind of figure out maybe some of these more complex problems. I wouldn't go crazy trying to figure out and understand stuff from it, because obviously it's a stats focused, and it's a stats book, right? And we're not learning stats here in this class. It's just very basic probability. But if it can give you at least some kind of idea or some kind of direction, if you're totally lost, then that's a win. So what was it called? Yeah, go ahead. Mm-hmm. Okay, no worries. Yeah, I was about to say, I was like, oh shoot, I have to go back and redo it then. Yeah. second. No worries at all. Go ahead. So for RMS speed, it's specifically referring to the square root of the average speed squared with the exponent inside the bracket, basically. And so I don't know, like, they really never gave us a specific term to differentiate between these two. I just say the one with exponents inside the bracket or outside. So for RMS speed, it's specifically the square root of the average squared where you do this function right here. So you take first your value, each value you square it, multiplied by the probability of finding each value, which is very similar to what you did here to find out the average speed. It's just that instead you took each value squared. So once you have that component, which is the average squared with the exponent inside the bracket, that's how you'd figure out that specific value. Then you take the square root of it, and that gives you RMS. Now, there's also this value, which is the average with the exponent on the outside. When the exponent is on the outside, that's just meaning that you're taking whatever average you have here at the end, so that's 474, and then squaring it. So you take 474 squared. That would be, let me just to show you the difference. So 474 squared, right, is 224,676, basically, right? So this, when the exponent is on the outside, is 224,676, right? As opposed to when it's on the inside, right? If we were to calculate this out, so 518.8 basically, and if we square that, I think, right, you get like 269 153, right? So there's a clear difference here. The difference is when it's outside the bracket, this exponent is outside the bracket, it means that first you take the average, then you square your final answer. When the exponent is on the inside, right, that means you square the values from the beginning before you get your answer. So you square each value, multiply by the probability, and then whatever your final answer is, well, that's your final answer, right? So that's the difference between those like two values there, where the exponent is on the outside. When it's on the outside, it means you take your average first, then you square your final answer. So we did the average, right? We did 474, then we squared it at the end if we wanted to get the average squared with the exponent on the outside. Now, when the exponent is on the inside, it means that you take each value, you square it first, multiply the probability, sum everything up, and then that answer gives you the 269, 153, right? So that's why there's a difference between them. There's a difference between taking or squaring at the end versus squaring at the beginning. And so your RMS then is asking for, okay, well, what's the square root of you squaring things from the beginning, right? That's the idea. So VRMS is taking the square root of this second average squared, where you squared things from the beginning instead at the end. Does that make a little bit more sense? They wouldn't even do wording. They would literally just tell you what's this. Like, they would literally just ask that. Or like, you remember for problem 3 where they were asking like compute these values here. They would literally just say compute this or compute that. They wouldn't even bother with like, oh, what's the one with the exponents on the outside or the inside? Like, I'm just trying to differentiate or distinguish them just to make things a little bit easier to understand. But like, they never even said it in the slides. We never learned it. I'm not sure. I should probably look it up, to be honest, but I didn't really find any distinguishing like term between them, because they're both like the average squared, but like one is you average at the end and the other one is you average from the beginning. or you square them at the beginning, I mean. But yep, no problem. For some reason, I cannot find this freaking stats book. I can't find the name of it. Hold up. Yep. It would have to be in the bracket, but for some reason I just kept it consistent with the equations in the slide because that's what you're gonna see, and that's the distinguishing factor that I mentioned earlier is that you might see it as this on the equations on the slides, where the squared is on the outside, but what it actually means is that this is your RMS speed. It would just literally be saying like VRMS and then you square it. Oh, it does have. Okay, then maybe my slides are just wrong and they fixed it. So I apologize then, because I went consistent based on my slides. So, but yeah, so I guess they fixed that mistake then. Yep. Wait, say that again. Wait. So you're talking about like the 474? Yeah. Exactly. Yep. No worries. No, that's absolutely right. Yeah, you just take the 518 squared, which is that 269 or something. Yeah, you can plug that one as well, and you can just do the 269. That would be the same thing because VRMS, if you take that squared, it would give you what's going on here. This one right here. If you take the VRMS and square it. But yeah, for some reason I just went by the equation sheet that they gave us for our year, and they have the square root or the square on the outside, and so we just did the 518.8 and then squared it, which is the exact same thing as just the average squared, which would have been VRMS squared. But yeah, it's like the whole like inside outside the bracket is just difficult. No, for this you didn't have to. Like you kind of solve for it anyway because you take the square root of that thing to get your VRMS. But if you just do this one big long equation, right, you never actually come up with the value of 269, 153. Oh, no. They didn't ask you for that. Yeah, for the average, yeah. Yeah, I mean, if I have the squared on the outside, then it would just be the 474 squared, so. Oh, just V bracket. No, just V bracket. Because they're just asking for the average speed. No. This was just me like explaining to Rachel a couple minutes ago. But they're just asking for average speed. My bad. Yeah. It should be just in meters per second. Otherwise, it would be like meters squared over second squared, essentially. Yep. No worries at all. yeah, I for some reason I can't find this stupid stats book, but it's so good. Um, Once I find it, I will let you guys know. But other than that, honestly, this is probably it for the night. I'll probably send in the name of the book in the group me or something, just so you guys have access to that as well. But if there's no other questions, then I mean, we could either call it a night or you guys might have other questions. I don't know. Mm-hmm. Yeah, if you use so you could either do 518.8 squared, right? Because that would just be your that would be saying like your RMS squared, or alternatively, it would just be it's just literally the same thing. It would be V squared like this, and so that would be this whole part without the square root, like this inside here, which would be the 100 squared times 0.06 plus 300 squared times 0.34, right? That whole long-winded equation there, that would be the answer that you get. That would be like that 269,000 something that we came up with earlier. But otherwise, you can just take your RMS and then square it. Yep. Oh no, yeah, for 100% that we've done it in AP Stats. That's why like I really want to remember the name of this book. For some reason, I just can't remember it. Like I remember what it looked like. I know the front cover. I just can't remember. It was like The Life of Stats or something like that. Yeah, yeah, I can pull it up. Yeah, exactly. And they had to have like the value right in the middle. Oh, okay. Now I just remembered it. It's called The Practice of Statistics, and it's the fifth edition. Dang. Okay. If I would have remembered that literally like 2 minutes ago, we would all have been in a good position. Hold up. 'Cause I remembered it had like flamingos on the front cover or something like that. Yeah. So let me link the. There we go. So copy and paste. There. Hopefully you guys can see that. That's the book I'm talking about. Practice of Statistics, 5th edition for the AP exam. There's a chapter there, I think it's chapter 5 or chapter 6 about probability. Very excellent. Yeah, I know, isn't it awesome? Like I swear like it's a good book and it's very easy to follow and everything. But actually, mhm. Yeah, no, it's a great textbook. Ah, I gotcha. Give me 1 second here. Actually, I'll end the recording. So this is just the end of the review session for those that are watching online, and yeah, hopefully this helped.